Let's go through some concept questions. Go ahead and read through this. All right, the correct answer is C. That can be explained either by Newton's third law that we learned earlier. For every action, there's an equal and opposite reaction. Or it can be explained by this equation to calculate the force of gravity, this attractive force between these two planets. We would need the value of the mass of both planets. And that's true regardless of which planet we are calculating the force for. So both reasonings apply. Let's look at another question. What do you think about this one? Correct answer is A. This is where that inverse square law comes into play. Since the gravitational attraction inversely depends upon distance squared, I just have to think about changing this distance, doubling it. But since I'm squaring that, the force is going to be 1/4 of what it was before if I've doubled the distance. So the new gravitational force will be 1/4 of that 1 million newtons. So A is the correct answer. Another question for you. What do you think about this one? Correct answer is B. Now, free fall, remember we're talking about the acceleration of gravity. So ultimately, we can say that the acceleration of gravity is equal to capital G, the constant, the mass of the planet, and then the radius of the planet, when we're talking about the acceleration of gravity on the planet. So here, our new planet has twice the mass and twice the radius, which that radius needs to be squared. So we end up with the 2m over r squared, 2/4. So we end up with 1/2 of the original g. Okay, if you want to see this a little more specifically, I could say g of planet X is capital G m over r squared. G for planet Y, I would put in twice the mass of planet X. So I'll put my x's up here for G of planet X. And then twice the radius of planet X. For radius of planet X. So we get the 1/2 times the big G mass of planet X over radius of planet X squared. But this is G of planet X. This is where we're getting G of planet Y is half of G of planet X. Okay, I have another one for you. What do you think about this one? Correct answer is B. This is just like throwing a ball. On Earth, we're standing, we throw a ball. The velocity of this ball and the acceleration it experiences after it leaves our hand are independent. Whether I threw the ball or just dropped the ball, the acceleration of gravity depends upon the Earth itself, not the ball. So Mount Everest, we could essentially ask this question, asking about the acceleration if we were dropping a ball at the top of Mount Everest, as opposed to throwing it. Now, this thought process, though, is interesting. It's one of Galileo's thought processes. So zooming in, if there was no atmosphere, this ball would go under projectile motion. So depending upon how fast it was thrown, it would experience both a horizontal motion parallel to the ground and a vertical motion because of the acceleration of gravity. And so the thought was, well, if I throw it faster, it will land farther, which makes sense. Ultimately, the thought process, well, if I was to throw it fast enough, it is falling towards the ground and moving horizontally relative to the ground, but the ground itself is not perfectly flat. And so the curvature of the Earth makes it such that the Earth is never in the way. It's not there. And so the concept behind orbits, getting something into orbit, is to launch it fast enough so that even though it has motion parallel to the ground and it is experiencing the acceleration due to gravity, the curvature is such that the Earth's surface curves as well, and then the ground is never in the way. And we end up with an orbit of some sort. We will talk about circular orbits in the next slide. Orbits, of course, are not all perfectly circular. Some of them are elliptical. It depends upon the speed of the object, which we'll talk about in the next video. Okay, another question. What do you think about this? Correct answer is C, a bit less than pre-launch. If we think about weight that we've been calculating all along so far this semester, we've been using mg. So if we're assuming the mass is essentially the same, it's g that really we care about. We can find the acceleration due to gravity that the space station experiences because of the pull of the Earth. We would need the mass of the Earth and the radius of the orbit because it's the distance from the center of the Earth to the center of mass of the space station. So we already know G, it's a constant. The mass of the Earth, we pull off the test notes. R, well, it tells us the orbit is about 200 kilometers above the Earth's surface. So to approximate R, we're going to take the radius of the Earth, just the average value, because that's what we've been given in the table, in the test notes. So this is an approximation. And we're going to add this height this approximate 200 kilometers above the Earth. So the radius of the Earth we have is 6.37 off the table, times 10 to the 6th. The height of the orbit, so 200 times 10 to the 3rd. I'm going to add these together. So r, in our equation to calculate the acceleration due to gravity, ends up being 6.57 times 10 to the 6th. So now if I go ahead and plug these values in, I'm getting 9.24 meters per second squared. Now it's certainly not 9.8, but in terms of the options I have, the weight, when I multiply the mass of the space station times this value of g, it's not going to be a whole lot less. So it's not 0, and it's not a lot less. It's not almost 0. It's actually still fairly close to 9.8. It's closer to 9.8 than to 0. So that's something that is a bit conceptually hard to understand. This force of gravity has far, far reaches. And so we have to be extremely far from the Earth to not experience a force of gravity towards the Earth. Here, the space station is not far enough. But again, the space station orbits because of the force of gravity. So we're using the force of gravity to allow this orbiting to occur. Okay, one more concept question. The correct answer here is E. There's definitely gravity. We just showed that in the last question. The space station is experiencing an acceleration due to gravity of 9.24 meters per second squared. We calculated that in the last problem. So as the space station is orbiting the Earth, both the space station as well as the astronauts inside are experiencing this acceleration due to gravity. The acceleration due to gravity is due to the Earth and how far from the Earth we're talking about. It is not due to the people, it's not due to the space station. So the space station has a velocity, but it also is going to be going through this projectile motion because of the acceleration due to gravity. As the space station continues, ultimately, we get this free fall. If you remember, again, the definition in physics definition of free fall is moving under the influence of gravity. So both the space station and the astronauts are in free fall around the Earth. So if both the space station and the people inside are experiencing the same acceleration, then there's no normal force. The concept of weightlessness is having no normal force. The floor of the space station, whichever side that may be, cannot exert a force on the astronauts if the astronauts and the space station are accelerating at the same rate. So they both are experiencing a gravitational force. It's the same idea. If you've ever been in an elevator and right before, immediately at the moment the elevator starts to accelerate downwards, if you jump immediately as the elevator starts to accelerate downwards, you get a very brief feeling of weightlessness. Your feet have left the floor, but the elevator has also started moving down. And so you have a very brief feeling of weightlessness. It's not that you don't have weight. It's not that the earth's not pulling on you. It's that your feet are not in contact with the floor. And so you just have that really brief feeling of weightlessness. So the concept of being weightless is a feeling and interaction. We're not interacting with a surface to have a normal force. It doesn't mean necessarily that there's no force of gravity at all. So an interesting concept. If, which of course we would never want it to happen, if the cables holding the elevator broke. So we're in this tall building, we're up high, the elevator car would accelerate downwards at 9.8, but you or us, whoever we are in the elevator, would be accelerating downwards as well at the same rate. And so we would not have contact between our feet and the floor of the elevator, but we would certainly be falling to the ground, which of course we don't want this to happen ever, because the end result would not be good, because we would hit the ground eventually. So concept of weightlessness, there's no normal force. It does not mean there's no gravity. And so we're going to talk more about orbits in the next video.